Hello and good afternoon friends, welcome to CEC live lecture. Dear friends, today in this session we are going to talk on a new series. Dear friends, from today onwards we are starting a series, and this series is on basics of quantum mechanics. So this is the first lecture in the series, and we believe that from today's session you are going to get more and more of knowledge on quantum mechanics. Dear friends, for this session we have with us in our studios Dr. Sonia Bansal. Dr. Sonia Bansal is assistant professor in YMCA University. Dear friends, if you want to ask questions on quantum mechanics from Dr. Sonia Bansal, then you can call right in the studio. You can contact us through our toll-free number. Our toll-free number is 1-800-110-430. Our toll-free number is 1-800-110-430. So let's welcome our guest, Dr. Sonia Bansal, and let's try to grab maximum knowledge through her experience on quantum mechanics. Hello, ma'am. Welcome to the lecture.
Okay. Today I define about the basics of quantum mechanics. To define the quantum mechanics, first we discuss why we require the quantum mechanics. There must be a failure in the classical mechanics, then the quantum mechanics came into the account. What was the classical mechanics? Classical mechanics applicable only for the macroscopic bodies. If we talk about the classical mechanics for the microscopic bodies, it could not explain the many phenomena of the microscopic bodies. So we require the quantum mechanics to explain the microscopic phenomena such as photon atom scattering and flow of electrons in the semiconductor. Means if we define the behavior of microscopic bodies, then we require the quantum mechanics. Quantum mechanics basically is a collection of the postulates based on a huge number of experimental observations. The difference between the classical and quantum mechanics can be understood by examining both the classical point of view and the quantum point of view. First we discuss about the classical point of view, then why we require the quantum mechanics. If we talk about the Newton's mechanics, the laws are written in terms of practical trajectories. Then a particle, if we are talking about the classical point of view, then we define what is a particle? A particle is an individual mass point object that has a variety of properties that can be measured, which we call observables, and this observable specify the state of the particles. Means we define the position and momentum of that particle in a particular frame. What is a system? A system is a collection of particles where all the particles are defined, which interact among themselves via internal forces and can also interact with outside world via external forces. The next word is the state of system, in which we define the particle. What is a state of system? State of system is a collection of states of the particles that comprise the system. All properties of the particle can be known to infinite precision. What are the conclusions in the classical point of view? If we talk about the trajectories, it defines the state descriptor of the Newton's physics. And evolution of the states uses the Newton's second law. And if we define the principle of causality, then two identical systems with the same initial conditions, subject of the same measurement, will yield the same result. Now, on the basis of quantum point of view, we define a particle. Quantum particles can act as both particles and waves. Means we define the wave-particle duality in the quantum physics. Quantum state is several possible outcomes of measurement of physical properties, and all properties depend upon the probability. Probability means random chances we consider. Why we consider the random or the probability? An observer cannot observe a microscopic system without altering some of its properties. Neither one can predict how the state of the system will change. So we require the probability theory to define the state of a system. And the most important point to define a particle in a quantum point of view is the quantization of energy, which is the basic property of the microscopic particles. Means microscopic particle should be quantized. Basics of quantum mechanics, the Heisenberg uncertainty means principle, means we are defining a particles and we define the momentum and its position. If one cannot unambiguously specify the values of the particles, position and its momentum for a microscopic particle, that is delta x t naught into delta p, that is a momentum and that is a position at t0 with respect to any time, must be greater than equal to 1 by 2 h by 2 pi. What is h? H is the Planck's constant here. Means position and momentum are therefore considered as incompatible variables. The Heisenberg uncertainty principle strikes at the very heart of classical physics, means it defines the particle trajectory. The correspondence principle in the quantum mechanics, when the quantum physics is applied to the macroscopic system, means we apply the quantum mechanics as we try to apply the classical mechanics into the microscopic. Similarly, the quantum physics is applied to the macroscopic system, then it must reduce the classical physics. Therefore, the non-classical phenomena such as uncertainty and duality must become undetectable if we use the quantum physics for the macroscopic system. Niels Bohr confined this requirement into the correspondence principle, means here we are having the quantum physics and we approaches to the classical physics, then laws, physical models, predictions could not be explained by the quantum mechanics. Then after that, the particle wave duality, as we talk about the quantum physics, then we talk about the particle wave duality, where the behavior of microscopic particles is very different from that of the classical particle. Why? In some experiment it resembles the behavior of classical waves, but it is not localized in the space. In other experiments it behaves as a classical particle but it is localized in the space. The theory of light treats light as though it were composed of particles but cannot explain diffraction and interference in the classical. Maxwell theory of the electromagnetic radiations can explain these two phenomena, which was reason why the theory of light was abundant. Then we define the particle wave duality, where we define the particle as a wave and particle as a wave as a particle and particle as a wave. To define the waves as a particle, the Max Planck worked on the Blackbody radiation, in which he assumed that the molecules of the cavity wall described using a simple oscillator model and can exchange only the energy in the quantized unit, in the packets of the unit. In 1905, Einstein proposed that the energy in an electromagnetic field is not spread out over a spherical wave front, but instead it is localized in individual clumps quanta. Each quantum of frequency n travel through the space with the speed of light, carrying the discrete amount of energy and momentum. Means photon is used to explain by the two phenomena, means photoelectric effect and X-ray experiment of the Compton. It is Compton effect. If we come on the particles as a wave, then double slit experiment, in which instead of using the light source, one uses the electron gun to define the superposition principle. The electrons are diffracted by the slit and then interfere in the region between the diaphragm and the detector. And now here one by one we define the two properties, particle properties of a wave. First we take, in which we define, first we discuss about the electromagnetic spectrum. Here we are having a different frequency and different wavelength of radiations. Radiation type, here we define the wavelength, and here in terms of the frequency. The radio frequency of the wavelength 10 power 3 meter, then microwave 10 power minus 2, then we come on the infrared radiations having the 10 power minus 5 meter wavelength. Visible 0.5 10 power minus 6 meter range, ultraviolet 10 power minus 8, X-rays 10 power minus 10 and gamma rays 10 power minus 12. Here the frequency increases and the wavelength decreases as we move from radio to gamma rays. And similar manner, here we define the temperature of the object at which this radiation is the most intense wavelength emitted. This spectrum defines the different wavelength and different frequency of the radiations emitted. Particle aspect of the radiation. In the classical physics, the particle is defined by the energy E and the momentum P, and the waves is defined by its amplitude and is the wave vector K. But in the quantum, particle E defined by the charge, mass, laws of particle mechanics, waves defined by the electromagnetic waves, where we define the diffraction, interference, polarization, etc. This is the superposition principle. Here we consider the superimposition of the waves. A characteristic of the properties of all waves, where we have that two waves are interfere each other and they constructively interfere, then the bright light is formed. And when it is destructively interfere, then we can get the dark light. Here it travels extra distance x in the constructive interference, but here in the destructive interference, the extra distance travel by 1/2 lambda, means define the part difference in the constructive and in the destructive interference. And this is a superposition of the waves to get the interference pattern and diffraction pattern. The Young's double slit experiment, light consists of the waves, where we define the black-body radiation. Black-body, what is a black-body? A ideal black-body is a material object that absorbs all the radiations falling on it, means absorb all the wavelength of light which is falling on this black body, and hence it appears as a black under the reflection when illuminated from outside. Only the quantum theory of light can explain the origin of the black body radiation. When an object is heated, it radiates electromagnetic energy as a result of the thermal agitation of the electrons in its surface. This is a diagram of the black body. Here we see that in the diagram, this is a chamber where all the wavelengths fall upon in it, and here it absorbs all the wavelength. The black body radiations leaving the hole of a heated hollow cavity, or the radiation emitted by the black body when it is heated. This is the experimental result which we got when the black body is heated. Then this is the graph between the energy versus spectral energy density U nu d nu. Here in the diagram we see that in the graph the frequency at a particular point is 0, and as the frequency this is the spectral energy density, means spectral energy increases as the frequency increases, and at a particular point the frequency increases and we get the maximum energy. This point where we are having the maximum energy, and as the frequency increases the energy decreases, and here this is a visible region where we define the light, and these two curves has been taken at the different temperature. This is for the 1200 Kelvin and this is for the 1800 Kelvin, and this result is yet to prove theoretically. Then Planck defined it theoretically, that the energy distribution with respect to the frequency, and at a different temperature it has been calculated. The radiation inside a cavity series of standing waves. The density of standing waves in the cavity is defined by 8 pi nu square d nu by c square. The classical average energy per standing wave is defined by E is equal to kT. K is the Boltzmann constant and T is the temperature. Then Rayleigh-Jeans formula is used, where U nu d nu is equal to E g nu d nu is equal to 8 pi kt, here we put the value of E, then 8 pi kt c square nu square d nu for whole the system we are considering here. The Rayleigh assumption is standing wave can exchange any amount of energy with matter, and this graph has been taken after the theoretical calculations. Then classical mechanics define only the continuous energy distribution, but in the quantum it was defined as the discrete distribution of the energy. It was explained by the Planck's formula. The energy exchange between the radiation and matter must be discrete. And energy of radiation is defined by E is equal to nh nu, which is defined by the quanta or a packets of light. Then average energy per standing wave is defined by E is equal to h nu divided by E h nu divided by kt minus 1. Then Planck's modification has been done in that. Then we define the u nu d nu is equal to 8 pi h by c square nu cube d nu e power h nu divided by kt minus 1. That terms has been taken and putting the value from the previous equation, where the h is equal to 6.626 10 power minus 34 joule second. And this is used to define the energy distribution in the theoretically calculation. Here we define at the low frequency we have h nu, which is very less than equal to kt. Then the term 1 by E h nu by kt minus 1 will reach to 1 by 1 plus h nu divided by kt minus 1, then which is equal to kt divided by h nu. Then we put this value in the previous equation. Then we have u nu d nu is equal to 8 pi h by c square nu cube kt h nu d nu. And finally we get the equation which was explained by the Rayleigh genes. The value of it is 8 pi kt c cube v square d nu. If we talk about the high frequency, then h nu is very greater than equal to kt, means we are talking about this part. This part here, the high frequency h nu very greater than kt, then e power h nu divided by kt approaches to infinite. Hence u nu d nu approaches to 0. This value is going to be 0. Then mode per unit frequency per unit volume. This is a graph which defines the classical aspect and the quantum aspect, where the probability of occupying modes defined, where the average energy per mode is defined. If we come in the classical, then the value is 8 pi nu square by c cube, and similarly here in the quantum 8 pi nu cube divided by c cube equal for all modes. But here in the quantum, quantized modes require h nu energy. The every quanta or every packet of energy contains is h nu, and energy to excite upper modes less probable. And then here the average energy per mode we are defined by kt, but here defined by h nu divided by e power h nu k divided by kt minus 1. Then particle properties of the wave, experimental confirmation has been done by the three processes. One is the photoelectric effect, second is the Compton effect, and third is the pair production. One by one we define these effects. First we talk about the photoelectric effect. What is a photoelectric effect? Photoelectric effect basically a phenomena of ejection of electron from the surface of a metal when a light of suitable frequency strikes on it, and it is called the photoelectric effect. And the emitted electrons are called the photoelectron, and the effect is called as photoelectric effect, and it is defined by the Hertz in 1887, and then later it was explained by the Einstein in 1905, which provides the direct confirmation of the energy quantization of light. It was during the study of the electromagnetic waves that the ultraviolet light when fall upon to the metal, it is sparks coming off. Then the generation of the photoelectric effect took place. In the experimental diagram, we have the time between the incident and emission of the photoelectron is very small. Immediately the electrons will eject from the metal surface, and that time is very less, which is less than equal to 10 power minus 9 second. In the classical, the rays intensity more electrons independent of the frequency. What observed? No electrons below the threshold frequency will be ejected out. Here we see in the diagram that here this is a cavity where the metal plate, the radiations fall upon this metal plate, the electrons are ejected and deposited on the another plate, and this is the evacuated tube and voltage and current supply. What was the result of this experiment? The result of this experiment that if the frequency of the incident radiation is small, if the intensity of incident radiation is smaller than the metal's threshold frequency, then no electrons can be emitted regardless of the radiation's intensity. And in the second case, if no matter how low the intensity of incident radiation, electrons will be ejected instantly the moment of the frequency of the radiation exceeds the threshold frequency. In the third point, at a fixed frequency, the number of ejected electrons increases with the intensity of the light but does not depend on its frequency. The kinetic energy of the ejected electrons depends on the frequency but not on the intensity of the beam. The kinetic energy of the ejected electron increases linearly with the incident frequency. Then Einstein interpretation about the photoelectric effect, then which define that light comes in a packets and having the energy E is equal to h nu, that is known as a photon. An electron absorbs a single photon to leave the material. Then work function is defined by W is equal to h nu naught, which is the initial value to eject the electron from the metal surface. Larger W needs more energy needed for an electron to leave. Then classical physics fail for dependence of the effect of threshold frequency. Then nu naught is the threshold frequency, that much frequency is required to eject the electron from the surface. Then photoelectric effect defined by K is equal to h nu minus W, which is equal to h nu minus the value of W is h nu naught. Then here we put the value of h nu naught. Then the stopping potential at which all the electrons will be turned back before reaching the collector. Then we define Vs is equal to h nu by E minus W by E, and its value is hc by E lambda. We replace the nu by C by lambda minus We. Then here we see in the diagram that the energy E h nu naught is strike on the metal and the kinetic energy is 0 when the electron is ejected. Then energy is equal to h nu and the kinetic energy maximum is defined by h nu minus h nu naught. On the basis of that, we just do an exercise. We solve an example that when the two UV ultra visible beam of ultraviolet light of wavelength lambda is equal to 280 nanometer and the second wavelength is 490 nanometer fall on a lead surface. They produce photoelectrons with maximum kinetic energy 8.7 electron volt and 6.67 electron volt respectively. Then calculate the value of Planck's constant, and in the second part calculate the work function and the cutoff frequency of lead. As we know, K1 is equal to, here we consider the two wavelengths, so we use K1 is equal to hc by lambda 1 minus W, and here K2 is equal to hc by lambda 2 minus w. Now we can solve it. H is equal to K1 minus K2 divided by C in both the equation, and lambda 1 lambda 2 divided by lambda 2 minus lambda 1, and use 1 electron volt is equal to 1.6 into 10 power minus 19 joule. Then we can get 6.62 into 10 power minus 34 joule second. That is the value of the Planck's constant. Now calculate the work function and cutoff frequency lead. Work function will be defined by W is equal to, as we know the value of H, then C we know, then lambda 1 minus K1. K1 the value is defined here, then we put the value, then its value is minus 4.14 electron volt, and on the basis of that the cutoff frequency of the metal is defined by as W is equal to H nu naught. Then we will define nu naught is equal to W by H, then the value is 10 power 15 Hertz. Then is it possible of the reverse? Means here the photons fall upon a metal surface and electrons are ejected, and then it is possible that the electron will fall and the photon will be ejected. The reverse was defined by the Compton effect. The photon transfer energy to the electron, that is the photoelectric effect. Can reverse be true? Yes, we defined by the X-rays, where EM radiation with the 0.01 to 10 nanometer range, and it is defined by the X-rays. And here we see that heated cathode, the electrons will eject out and X-rays will be produced, where X-ray production lambda minimum is defined by 1.24 into 10 power minus 16 divided by V. And here defined by the platinum, the curve is defined by the platinum, where the frequency is defined in the range of, the wavelength is defined in the range of 0.01 to 10 nanometer. Now the Compton effect, the further which is used for the confirmation of the photon model. In 1927, Compton defined the Compton effect, where the Compton scattering is another one of those important event that happens at the beginning of 21st century that indicated that photon were real, and they really does and behave like a particle. Here we see in diagram the large wavelength fall upon a metal and small wavelength, and collision takes place, and this is a diagram where the scattering has been taken place. Now incident photon fall upon a target electron, and these electrons are, the scattered photons are ejected, and this is the scattered electron, and here we are having the different frequencies. The incident photon having the energy E is equal to h nu and P is equal to h nu by C. Target electrons having the energy E is equal to m naught C square, then P is equal to 0. Then scattered photon of the energy h nu dash and momentum h nu dash by C at angle phi and angle theta, the scattered electrons will be generated, and its energy is equal to root of m naught square C power 4 plus P square C square, where P is equal to and momentum is equal to P. The scattering of X-ray from electron in a carbon target and found scattered X-ray with a long wavelength than those incident upon the target. And in the diagram here we see that the scattering of the photon and the electron takes place when the incident photons strike upon the electron. Thank you. welcome back. We are talking about the Compton effect, where the incident photon strike on the target electron and the scattered photon and the scattered electrons generated with the different frequency and the different momentum and the different energy. And here we define that h nu dash by c is the h nu is the momentum, and here momentum for the target electron defined by the p. And if we take the triangle of here, then we can find out this part is the h nu dash by c cos phi, and this part is h nu dash c sin phi. And similarly here in the lower part, and talking about the target electron, then it is defined by p sin theta and defined by the p cos theta. Now we have got to know what energy of the photon is and what is its momentum. Means we define the energy and momentum of the photon which is ejected out after the scattering. The photon energy defined by the h nu and the photon momentum defined by h by lambda, or we can write it as E divided by C. In the collision, converse energy and the conserve momentum. The elastic process taken place here. In the original photon direction, initial momentum is equal to final momentum. The initial momentum defined by h nu by c plus 0, and final momentum defined by the h nu dash by c cos phi plus p cos theta. This is taken for the photon and this is for the electron, and this is the incident photon. Then we define in a perpendicular direction, theta is equal to h nu dash by c sin phi minus p sin theta. This is defined for the target scattered photon, and this is for the scattered electron. Now we define pc cos theta is equal to h nu minus h nu dash cos phi. Then we can write it as pc sin theta is equal to h nu dash sin phi. We solve this equation in a simple manner. Now we take the p square c square, means we are taking the we take the addition and the squaring of these two equation. Then we can get h nu whole square minus 2 h nu dash cos phi plus h nu dash ka whole square. Now from the total energy expression, we have p square c square is equal to h nu whole square minus 2 h nu dash plus h nu dash whole square plus 2 m naught c square h nu minus h nu dash. And then we define it as, by solving the equation, 2 m naught c square h nu minus h nu dash is equal to 2 h nu into h nu dash into 1 minus cos phi. Now the Compton effect or Compton shift is defined by delta lambda, which is equal to lambda dash minus lambda is equal to h by m naught c into 1 minus cos phi. In order to conserve energy and momentum, I have got the same shift in the wavelength. That means outgoing photon has a different wavelength than the incoming one. Both the photons are different. This is impossible classically. We cannot have a wave do that, but in quantum it can be possible. This shift in the wavelength is associated with h by mc. This is the dimensionless quantity. Then Compton wavelength defined by lambda c is equal to h by m naught c, which gives the scale of the wavelength change of the incident photon. H by mc is really small compared to the wavelength of light which is using. Then the shift in the wavelength is relatively very small effect if lambda is very greater than equal to lambda c. If lambda by mc is very large compared to the wavelength of the radiation, that that we are sending in the hit of the electron, then this shift in the wavelength is going to be huge. Then we can get the large Compton shift and the large effect, and which is defined by the if lambda is very less than equal to lambda c. So the Compton scattering is determined by how big the wavelength of the light that are sending to target the electron, and the comparison of the Compton wavelength defined. Then here if we take the angle of the electron, that is the angle of recoil electron, which is defined by the tangent theta, we define it as sin phi by lambda dash by lambda minus cos phi. And this is the experimental setup for the demonstration of the Compton effect. Here the source of monochromatic X-rays is used. This is the collimator to pass the X-ray beam, and this is the target. Basically the carbon has been taken when Compton done the experiment in 1923, that the carbon target taken, the X-ray fall upon the carbon, then the scattering of electrons takes place, and then here the X-ray spectrometer is used to calculate the scattered X-ray, unscattered X-ray, and the photon which are ejected. This is the path of the spectrometer, means spectrometer move in this 180 degree. And these are the observations which has been taken. Here the X-ray tube, molybdenum K alpha, carbon target, the X-ray fall upon it. Here the crystal, calcite crystal is used, light fall upon 90 degree at 90 degree, and here the ionization chamber and the record of the scattering from the outer carbon electrons. Here we see the crystal and ionized chamber rotate together to act as a Bragg spectrometer to measure the wavelength of scattered X-rays. And this is the graph which recorded. Then scattering from inner carbon electrons produces very little wavelength shift because they are tightly bound and the entire atom recoils. And in this diagram, at the different angles used, this graph has been taken at the 0 degree where we get the single curve. Then at the 45 degree this curve has been obtained, and the lambda dash, the value of lambda dash is equal to 0.0715 nanometer. The scattered wavelength is defined here. Then when the apparatus is put at 90 degree, then the lambda, the value of lambda is 0.0731 nanometer. And when it is at the 135 degree, then these two curves recorded, one at the 0.0709 and second is 0.0749 nanometer. This is the experimental setup of Compton effect. Now on the basis of Compton effect, let us try an example. Now high energy photon, means gamma rays, are scattered from the electron initially at rest. Assume the photons are backscattered and their energies are much larger than the electrons' rest mass energy E, which is very greater than equal to MEC square. Then first calculate the wavelength shift. In the second, show that the energy of the scattered photon is half the rest mass energy of the electron, regardless of the energy of the incident photons. Then third part, calculate the electron's recoil kinetic energy if the energy of the incident photon is 150 mega electron volt. Here phi is equal to pi. Wavelength shift or the Compton shift is calculated as delta lambda is equal to lambda dash minus lambda, which is equal to h by m naught c into 1 minus cos phi. Then we can have, which is equal to 2h by mec, and it can be written as 4 h cut c by m naught c square. Here it is multiplied by the h by 2 pi and c multiply and divided by the c, then the value of delta lambda calculated is 4.8 into 10 power minus 12 meter. All the value are given here. The mass of an electron, here the speed of light h dash is a Planck's constant, and energy of the scattered photon E dash is calculated by this formula. E dash is equal to hc by lambda dash, where the lambda dash is equal to h plus 2h by mec. Then we can write it as mec square divided by mec square lambda by hc plus 2, and this formula will become mec square by E plus 2. If E very greater than equal to mec square, we can approximate by E dash is equal to mec square by 2, 1 plus 2 mec square by E. The value of E is given, and here by solving this we have only the mec square by 2, and the value of this comes out 0.25 mega electron volt. Third part is the calculate the kinetic energy if the energy of the incident photon is 150 mega electron volt. Then kinetic energy of the recoil electron, which is defined by Ke, is equal to E minus E dash, and 150 mega electron volt minus that has been calculated is 0.25 mega electron volt, and which is equal to 149.75 mega electron volt energy is required to get the electron recoil. The third part is the pair protection. Now photon strike on the nucleus, then electron and positron will be ejected, and this is defined by h nu by c, and theta for the electron and this theta for the electromagnetic energy is converted into matter in the pair protection. The energy and the linear momentum could not both be conserved if pair protection were to occur in the empty space. So it does not occur. Then pair protection requires a photon energy of at least 1.02 mega electron volt, and E minus or E plus defined by m naught c square is equal to 0.51 mega electron volt, which is a rest mass energy. Then additional photon energy becomes kinetic energy of electron and positron. The pair protection direct consequences of Einstein mass energy relation, which is defined by E is equal to mc square. Then pair annihilation, then E plus means electron plus positron is defined by the energy gamma plus gamma. On the basis of that, we again solve an example, calculate the minimum energy of the photon so that it converts into an electron positron pair. Then find the photon's frequency and the wavelength. The E minimum of the photon to produce the electron and positron pair is equal to the sum of rest mass energy of both. So E minimum defined by 2me square, and which is equal to 1.02 mega electron volt. Now the photon's frequency and the wavelength can be obtained at once from E minimum, which is equal to h nu is equal to 2mec square, and lambda is equal to c by nu. Now the value of nu is equal to 2.47 10 to the power 20 hertz, and lambda is equal to 1.2 into 10 to the power minus 12 meter. The next part is the wave properties of particle. In the wave properties of particle, we define the light. Light has a dual nature, wave nature and a particle nature. If we talk about the wave nature, then we define the electromagnetic waves. If we define the particles, then we define the photon. Though to define the wave, then interference diffraction patterns are most common example to define the wave nature of the light. And to define the particle nature of the light, photoelectric effect and Compton effect, which we already discussed. The wave particle duality for the light is defined in terms of the when the light strike on the matter. What about the matter? If the light which was traditionally understood as a wave, also turns out to have a particle nature. Matter, which is traditionally understood as a particle, also have a wave nature. Means matter behaves as a particle and a wave, and here the light behaves as a wave as a particle. Light is a wave or light is a particle. Now, Louis de Broglie hypothesis. In 1905, light behaves like a particles. We define the momentum P is equal to h by lambda. In 94, matter behaves like a wave, and it turns out that everything's kind of mixed together at the fundamental microscopic level. Then the de Broglie wavelength defined by lambda is equal to h by p. H is a Planck's constant and p is the momentum of a particle. Then both the wave, if lambda very greater than scale, then particle if lambda is very less than scale, then particle and wave nature is defined by the light. Then hypothesis in 1924, and for this he got the Nobel Prize. Then idea is matter because the momentum is so large compared to the photon. Then the shorter wavelength. What is the de Broglie wavelength of an electron? That moving at 2.2 into 10 to the power 6 meter per second. An electron is moving with this speed 2.2 10 to the power 6, then what will be the de Broglie wavelength? Now this is really very fast, the 2.2 million meters per second, but it's not relativistic, it's still slow compared to the speed of light. So we can still do everything in the classically. Then P, momentum P is defined mv, where mass of the electron is defined as 9.1 to the minus 31, and v is given here 2.2 into 10 to the power 6 meter per second. Then the momentum P, which comes out 2 into 10 to the power minus 24 Newton second, and the lambda wavelength, which is equal to h by p. P we calculate here 2 into 10 to the power minus 24 Newton second, and then here h divided by p. The value of h is 6 Planck's constant, which is 6.626 into 10 to the power minus 34 divided by momentum, which and the value is 2 into 10 to the power minus 24. The value of lambda is, the wavelength is 3.33 10 to the power minus 10 meter. Now this is an important number. This speed, the kind of average speed of an electron in the ground state of hydrogen, and let's estimate for the de Broglie wavelength. For the free particle, we define the momentum by P is equal to mv, where v is the speed of the particle. For the free particle, the total energy E is the kinetic energy. Then we will define lambda b is equal to h by p, which can be written as h divided by mv, where the value of p is equal to mv, mass into velocity, is speed of light. Then we can write it as h divided by root of 2em. And here E, what is E is equal to K, which is equal to P square by 2m, and is equal to mv square by 2, which is the kinetic energy. And example, there are some example here. A bullet of mass 0.1 kilogram and speed is equal to 1000 meter per second, then lambda b is defined by the 6.63 into 10 to the power minus 36 meter. Electron at 4.9 volt potential, then mass is equal to 9.11 10 to the power minus 31 kilogram, then energy is equal to 4.9 electron volt. Then lambda b is defined by 5.5 angstrom. Both the values are different, and it depends upon the value of m and energy and or E. The wavelength of electron with 50 electron volt kinetic energy, K is equal to P square 2 me h square by 2 me lambda square, which is equal to lambda, and we define it as 1.7 × 10⁻⁻10 meter. The wavelength of nitrogen molecule at room temperature is defined by K is equal to 3 kT by 2, mass is equal to 28 and lambda is equal to h by 3 mkt and 2.8 × 10⁻11 meter. Now wavelength of rubidium atom of 50 and nk, then lambda is equal to h by root of 3 mkt and whose value is 1.2 into 10⁻6 meter. These are the different values and different values of wavelength and kinetic energy is defined for the electron, nitrogen molecules and rubidium atom. Now what is the difference between the particle and wave? Our traditional understanding of the particle is localized, definite position, momentum which is confined in a space. And what is the wave? Wave is defined by this curve and which is delocalized, spread out in a space and time, disturbance in the medium. This is the particle and this is the wave. These are the basic definitions of the particle and wave. Then how do we associate with the wave nature of a particle? What could represent both wave and particle? Then find the description of the particle which consists with our notion of both particle and the waves. Fits the wave description localized in the space. Then we define by the wave packet. The localized of the space means how do we construct a wave packet to define a wave. It means number of waves should be collected together and we can get the wave packets. Then the waves of the same frequency, what happens when the waves added? Then superposition principles takes place when the different waves, here we are taking the green wave, blue wave, red waves or different wavelengths, wave of the same frequency, then they collectively each other. Then adding up the waves of different frequencies, the waves of slightly different frequencies, the wave of, here the different frequencies waves has been taken, then they are combined together, then constructing a wave packet by adding up of several waves. If the several waves of different wavelengths, frequency and phases are superposed together, one would get a resultant which is a localized wave packet. Here we define the wave packet, not a single wave but the number of waves in a packet. And the wave packet describes a particle. Now we define the particle in terms of the wave packet. A wave packet is a group of waves with slightly different wavelengths interfering with one another in a way that the amplitude of the group envelope is non-zero only in the neighborhood of the particle. A wave packet is localized and a good representation of the particle is defined by the spread of the wave packet in the wavelength depends on the required degree of localization in the space, and the central frequency is given by lambda is equal to h by p. P is the momentum, h is the Planck's constant and lambda is the wavelength. Then what is the velocity of this wave packet? Then wave packet phase velocity and the defined by the phase velocity and the group velocity. The velocities of the individual waves which superpose to produce a wave packet representing the particles are different. The wave packet as a whole has a different velocity from the waves that comprise it. Phase velocity. The phase velocity is the rate at which the phase of the wave propagates in the space. Then what is the group velocity? The rate at which the envelope of the wave packets propagates. Then wave packets defined by the two velocities, phase velocity where the phase of the wave propagates in a space, and the second by the group velocity where the envelope of the packets propagates. Then the phase velocity, how fast the wave traveling. Here we see that the one wave is traveling and the wavelength is lambda along the x-axis. The velocity is a reference distance divided by a reference time. Then the phase velocity of the wavelength divided by period, which is defined as V is equal to lambda by tau. Tau is the time period. Since is defined by the frequency, F is equal to 1 by tau, then we can write it as the phase velocity is equal to F lambda. Then in terms of K, propagation constant, the K is equal to 2 pi by lambda, and in terms of angular frequency, omega is defined by 2 pi by tau, and which is equal to V is equal to omega by K. What is omega? Omega is the angular frequency, and what is K? K is the propagation constant. In the similar manner, we define the group velocity. The single wave we have constructed, this is the velocity at which the overall shape of the waves amplitude or the wave envelope propagates. This is the signal velocity. Here the phase velocity is equal to group velocity for the medium in the non-dispersive. The dispersion, phase velocity, group velocity depends on the frequency. Now see, the black dot here moves at a phase velocity. The red dot moves with the group velocity. This is the normal dispersion. Refractive index decreases with increasing the wavelength. Now here we see the dispersion, phase velocity depend upon the frequency. Here the black dot moves at a group velocity. This is moving with the group velocity, and the red dots move at the phase velocity. This is the dispersion, and refractive index increases with the increasing lambda. Now the wave packet and phase velocity and the group velocity. What is the relation between the phase velocity and the group velocity? The phase velocity is defined by Vp is equal to omega by k, as already discussed. Then omega value is E by h cut, and the value of k is equal to P by h cut, which is equal to E by P. Nu p is defined by E by P. Here we put the value of E, which can be written as mc square. The P's momentum is written by m nu, and is equal to c square by nu, or we can write it as c by beta, or Vp, phase velocity, defined by c square by v square, the velocity square of the velocity of light and the v. And the c is the velocity of light and nu is the velocity of the particle. Then Vg is equal to V. For the group velocity, Vg is equal to d omega by dk. We take the differentiation of that. Then we put the omega and the value of k in this E by h cut, P by h cut, and which is equal to del E by del P. Vg is equal to, then we define it as del E by del P, the value of E put here, then 1 by 2 P square by 2m, then P by 2m, and which is equal to nu. And in this manner we can solve the wave packets in terms of phase velocity and the group velocity.
With this note, thank you ma'am, thank you so very much. We believe that all the students who might have watched today's lecture would have benefited and would have studied quantum mechanics in detail. But dear friends, this is not an end. We are going to conduct more sessions as it is a series. We believe that this series would be beneficial for you in future also, because we are going to upload the concerning lecture, that is today's lecture, on YouTube, as well as future sessions also, so that you can access the lecture the number of times you want it. And afterwards, if you have any queries or if you want to ask question from Dr. Pooja Bansal, then do write, Dr. Sonia Bansal, then do write to us at info.cec@nic.in. We would love to solve your queries, and definitely when next time Dr. Sonia Bansal visits our studio, we will try to give answers to your questions. Till then, take care, goodbye. Thank you ma'am, thank you so much.